Very good morning. As you know, the course title is numerical solutions of ordinary and partial differential equations. So, the first lecture is I would like to give a little bit of motivation with respect to some examples. So, as you know, numerical, when we say numerical solutions of ordinary and partial differential equations, yeah, many times we try to take some examples and then try to solve analytically, but sometimes we may not get analytical solutions. So, then we look for numerical solutions, but then unless we have a rigorous analysis of what kind of methods work for what kind of problems, we cannot really go for trial and error. So, the main aim of this course is to learn different methods numerically how to solve ordinary and partial differential equations. So, the first lecture is motivation. So, let us see. So, as I mentioned, why do we require numerical solution? Yes, definitely one does not possess analytical solution in hand. So, the simplest example we can is interpolation. So, what is interpolation? Method of constructing new data points within the range of a discrete set of known data points. So, for example, you are given x and the corresponding function, and we would like to get, let us say, x in between say 2.5 or 4.7 or 6.8. So, whatever. So, the aim of interpolation is approximate. What is that? Interpolation is supports a method of estimating the function at intermediate points. So, f of x will be approximated by a polynomial. Once you get an approximate polynomial, you can get the function value at any point. Okay. So, the given data points have been approximated by a suitable polynomial. So, then wherever you want, we substitute the corresponding value and get the approximate value, function value at that point. Okay. So, now more or less the story remain the same even in case of solutions of ordinary differential equations. So, when I say the story remain the same, I mean definitely we also try to approximate the given ordinary differential equation and get the approximate solution. Okay. So, many problems come from real life applications. They have to be handled numerically, because as you know, real life situations are really complex. So, we have to handle them numerically. Maybe there are few examples which can be handled analytically. Okay. So, I would like to explain with some examples how we arrive at ordinary or partial differential equations. So, then how we take it further to solve numerically. So, the first example I have considered is very, I mean, in physics it's a very simplest kind of thing. It is conservation of mass. So, what do you mean by conservation of mass? You take any flow quantity, okay, so which we represent by a vector field V. So, any flow quantity which we represent by a vector field V, conservation of mass suggests that the divergence of the corresponding vector is 0, provided there are no sources and sinks. So, in case when you have source and sinks present, so then the divergence V is equals to the corresponding source or sink term. Okay. So, I have written here divergence of V equals to Q. So, where V is the vector field, so which represents let us say a flow velocity or a flux of a magnetic field etc., and Q is the corresponding source or sink term, of course, which depends on the spatial coordinates. Okay. So, we are considering the steady case, the simplest case, hence this is the form. So, when there are no sources and sinks, Q will be 0. Okay. Now, let us consider another physical concept, that is when a flow is irrotational, we represent generally curl of V is 0. As you know, curl of a vector represents rotation. Okay. So, when curl of V is 0, the flow is called irrotational. Of course, I am not describing the conditions under which an irrotational field can be expressed as a gradient of a scalar. There are some restrictions on the domain, like the domain must be simply connected, etc. So, I have not put it, but quote in quote under those restrictions, your velocity field V bar can be expressed as gradient of a scalar, where phi is a scalar. Okay. So, now, so when phi is a scalar function, this equation is this. So, you substitute V equal to grad phi in divergence V equals to q. So, then the left hand side, when V is grad phi, we get a Laplacian. So, Laplacian of phi equals to q. So, this is a PDE which is popularly known as Poisson equation. Okay. So, this is Poisson equation. So, when q is 0, so then the corresponding homogeneous equation is called Laplace equation. So, this is the Laplace equation. Okay. So, now whether it is a ODE, for example, this particular equation 3, whether it is an ODE or it is a PDE depends on the coordinates. For example, let us see the Poisson equation is del square phi equals q. Okay. So, now let us say we are talking about 3-dimensional complete 3-dimensional coordinate system x, y, z. So, then your Laplacian becomes dou square phi by dou x square, dou square phi by dou y square, dou square phi by dou z square equals to q. So, this is a PDE, and what kind of PDE? It is a second order PDE, right. So, now suppose your quantities depends only on one coordinate. So, that means any quantity f just depends on say function of x, then your PDE reduces to simply d square phi by dx square equals to. So, this is a PDE, whereas this is a ODE. Okay. So, these are few examples. That means, the same physical principle, that is conservation of mass, which is represented by Poisson equation here, depending on the coordinate system. For example, when it depends on 3 coordinates, we arrive at a PDE. When it depends just on one of the coordinates only, then we arrive at a ODE. Okay. So, now if q is 0, then we have correspondingly the simplest first second order ODE d square phi by dx square equals to 0. Okay. So, which can be obviously solved analytically, but depending on the complexity of the physical situation, we arrive at sometimes corresponding equations which cannot be solved analytically. Okay. So, let us come back to the Laplace equation. Okay. So, this is the Laplace equation. Okay. So, now as I mentioned, if the flow quantities depend only on one of the coordinates, okay, then this reduces to an ordinary differential equation. Okay. Yeah. So, as I mentioned, one may solve this analytically, okay, in simple situations, but sometimes it is very difficult depending on the coordinates, sometimes depending on the geometry, the analytical solution cannot be obtained. So, then we have to look for numerical solutions. Okay. So, the main aim of the course is to learn numerical solutions. Okay. So, now let us consider a second example. So, the second example is I have considered which is very popularly known as Fourier's law. So, this comes in heat conduction problems. Okay. So, what is that? Let us see. So, Fourier's law is law of heat conduction. The time rate of heat transfer through a material is proportional to the negative gradient in the temperature and to the area. So, q bar vector field, which is the heat flux, and this is related to the heat temperature in this form. So, this is K is the thermal conductivity of the medium, and grad T is the temperature gradient. So, this is very popularly known as Fourier's law. Now, one dimensional form. So, one dimensional form, for example, in x direction we consider. So, then q x is minus k dt by x. Okay. Q x is minus k dt by x. So, for example, if we consider a rod of length L, then the gradient can be represented like this, T 2 minus T 1, apologies, this should be a suffix 1. So, T 2 minus T 1 by L, which is minus 1 over k q x. Okay. So, now if you consider only this combination, T 2 is expressed like this. Okay. So, you just make a note of it, T 2 T 1 minus L by k q x. Okay. So, we will come back to this very soon. So, one can define an initial value problem as follows. So, the same Fourier's law. So, dt by dx is some constant times q of t x. So, I have considered the simple case 1 dimensions. So, if it is more than 1 dimensions, then accordingly this will be gradient, and this also depends on more than 1 dimension. Then we need at any coordinate what would be the initial temperature. Okay. So, why do we require only at one point? Why do we require only at one point? See, what is this? This is a as long as q we consider q as solely a function of t, then dt by dx equals to something, assuming this is linear, this is a first order ODE. So, now how many arbitrary constants exist in the solution? It is 1, because it is a first order ODE. So, therefore, one require one initial condition to solve this. Okay. So, if we define an initial value problem like this, then this star exactly suggests a solution, a kind of more or less T 2 is T 1 plus. So, what is this T 1? At a known x naught. So, correspondingly T 2 at some other x solution is given by this. So, this is a kind of a solution of the initial value problem. Okay. So, that means if you generalize, one would expect T 3 is T 2 plus. So, similarly, a general T n plus 1 is T n plus some incremental term. Okay. So, this is general motivation how an initial value problem may occur, and then correspondingly what will be the solution. Okay. Of course, this is a kind of approximation when we say T 2 plus T 1 etcetera, because the gradient has been approximated by this. Okay. So, now we are in a position to define IVP more formally. Okay. So, let us look at few examples before we define more formally. Okay. So, for example, dy by dx equals x plus y. So, this is a first order ODE. As I mentioned, we need how many initial conditions? Okay. We need 1. Why we need 1? Because this is a first order ODE. So, let us define your condition as, say, y of maybe 1 equals some quantity. So, this can be considered as initial value problem. Okay. So, similarly, one can consider examples, say minus x dy by dx, okay, plus x squared y equals, say, cos x. So, what kind of ordinary differential equation is this? Second order ordinary differential equation. So, now to solve it we need two conditions. Okay. So, let us say y of 0 is 0, then y of 3 is 6. So, this is also an initial value problem. This is also an initial value problem. Okay. So, we would like to consider such initial value problems and devise numerical methods to handle them. Okay. So, before we define more formally, so when we say numerical method, how do we arrive at a particular numerical method? What is the motivation? Okay. So, I would like to explain with reference to a simple method which is a kind of semi analytical. So, why do I say semi analytical is it is not really numerical, but it is numerical. So, it is definitely interesting because any numerical method we expect a kind of iteration. Okay. So, what do you mean by iteration? You plug in something and then get an improved version, then again you plug in that process and get improved version, so on, so forth, right. So, let us consider one such semi analytical method which suggests what is a numerical solution. Okay. So, let us see that. So, I will explain with respect to an example. Okay. So, the example I consider is dy by dx is 1 plus y square. So, as I mentioned, this is a first order ODE. So, I need one condition. So, I have taken this condition as very simple, right. So, this is initial value problem and first order. Okay. So, now when I said semi numerical, okay, that means to some extent we proceed analytically and then we switch over to numerical. So, that is the motivation. Okay. So, you integrate, okay, integrating say this is a star, integrating star from x naught to x. So, some x naught. So, it will be x naught to x, okay, dy by dx equals integral x naught to x 1 plus y square dx. Okay. So, this is the step. So, which is definitely analytical. Okay. So, now let us expand this. Okay. We integrate dy by dx. So, that we get it as, okay, y of x minus y of x naught equals integral x naught to x 1 plus y square dx. Okay. So, this is if you perform the integration on the left hand side, we get this. So, this can be written as y of x equals y of x naught plus okay. So, now at this stage, if you look at it, the corresponding differential equation has been reduced to an equation which involves an integral. Hence, you may call this is an integral equation. Okay. So, now next question is how do we solve it? Remember, we have not yet made use of the initial condition. Okay. So, now how do you solve it? If you look at it, right hand side also contains y. We are looking for y, whereas right hand side also contains y. So, therefore, how do we proceed further? Okay. So, this is where I defined this method as semi numerical, because now we cannot proceed further in some sense analytically. So, therefore, we would like to bring in the numerical concept in the sense a kind of a iterative process. Okay. So, in order to solve, say this is this. Okay. So, in order to solve, okay, we suggest an iterative method. Okay. So, what is the iterative method? We have our initial condition in hand, right, which we have not yet made use of it. Okay. So, we would like to pick up that initial condition and see left hand side we are trying to obtain. Okay. So, that should be our answer, right. So, whereas right hand side contains the same quantity y. So, therefore, what is an iteration? As I mentioned, whatever approximation in hand you put it in your process and get a slightly refined version, then put that in the process and get slightly refined. So, now here we have right hand side y. Now, we plug in our initial value as a first approximation. Okay. So, let y 0 of x equals y of x 0. Okay. Right. Okay. So, this is our initial approximation. So, now for this problem y 0 is defined as 0. Okay. So, let us see what will happen. So, y of x, which is y of x 0 and x 0 is 0, 0 to x, okay, 1 plus y square will be now y 0 approximation dx. So, now y of x 0 is 0, okay, 1 plus, and this is 0. Okay. So, this is simply x. Okay. So, we get a first approximation, therefore, we denoted this okay. So, we denote this y 1 x equals to x. So, now we expect that this is a refinement over the initial guess. Okay. So, now we would like to make use of this, okay, and get the next approximation. Okay. So, let us see how do we do it. So, we define y 2 x as y x 0 plus 0 to x 1 plus y 1 square. Okay. So, this is what we define. So, now what is our y 1? Y 1 is this. Okay. So, now we should plug in that in the right hand side. So, let us see. Y 2 x is y of x 0 0 to x 1 plus y 1. Okay. So, this is again this is 0 1 plus y 1 is x. So, this is plus, so this is x cube by 3. Okay. So, this is our y 2, this is our y 2. So, now we would like to improve upon this. So, how do we do it? Again define y 3 processor. To x 1 plus y 2 square. So, this is 0 1 plus y 2 is x plus okay. So, this is so, this is this is 7 into 9 plus so, this is what we get y 3. Okay. So, now what is the story next? So, we got the expression, right. So, why I said it is a kind of semi numerical. It looks as if an analytical method, because you are seeing only the expression so far, no numerics, but what is the motivation behind it? You get some initial approximation in hand, you plug in that, improve, and you get a refined version, plug in and get a refined version. So, this is a kind of numerical, whereas the expression in hand is looking like a analytical. Okay. So, what we would like to do now, suppose you need a solution at a particular point. So, since you have the expression, you definitely plug in, and in this whatever we have obtained, and you get the solution. But how do we know that this is really exact solution of the given initial value problem? Okay. So, there is an issue here. What is that issue? We have done up to 3 terms, that means we refined and we have obtained y 3, but one of your friend, let us say does it 10 times. So, then what do you expect? Yes, the number of terms will be more. Okay. So, naturally when you compute the value at a particular point using whatever just now we have obtained, and let us say your friend used 10 terms, means 10 refinements, and then the person gets a huge expression and get a value using that expression, then if at all you have analytical solution in hand and try to compare. So, the solution obtained by your friend appears to be more closer to the analytical solution. So, why is that? Because your friend used more number of terms. Okay. So, that means the moral is whatever we have obtained is not the complete analytical. So, there is a kind of a numerical process involved which is bringing in some kind of error. So, I would like to use this word for the first time. So, why do we say error? Yeah, it is obvious, we have used only 3 terms, right. So, then we got some value, but your friend used 10 terms and got a little refinement. So, that means you can compare, if you use 3 terms the solution and then use 10 terms, there is some difference, right. So, that is the contribution of the error if you stop after 3 terms. So, you can refine and then improve, okay, right. So, now is there any particular name given to this method? Of course, yes. So, it is popularly known as Picard's method of successive approximation, Picard's method of successive approximation. Okay. So, now the next question comes, definitely who would ensure that the method gives solutions which converges to the exact solution. Okay. So, that is the Picard's existence and uniqueness theorem. Okay. Who would ensure the convergence of the solution, that is Picard's existence and uniqueness theorem. Okay. So, I am not stating the theorem, however, you can refer the standard books given in this course. So, you can refer to know what is Picard's existence and uniqueness theorem. So, this theorem ensures that the solution converges. So, now what y 3 we obtained? Y 3 we obtained is x plus by 3 plus 2 x 5 by 15 plus x 7 by 63. So, an intelligent person would try to say, can we close it, like this appears to be a nice series. So, can we get a closed form expression, so that we immediately conclude that this is our this could be our exact solution. Yeah, fortunately the example which we have taken, it is supporting this. This is tan x. Okay. So, situations where the series supports a closed form expression, then we will be tempted to say this is a solution. However, numerically tan x, when it is expanded in any computer code, definitely one has to use terms up to certain number and then the rest will be thrown out. So, that is where I am defining those terms as error. So, we will discuss in more detail about what do you mean by error. Okay. So, now in situations where we cannot get such closed form, obviously we have to say that this is the solution. Okay. So, for example, now somebody would like to get at 6. So, we substitute in the corresponding expression. Okay. etc. Okay. So, now are we in a position to define a general? Yes, of course, we are in a position to define the general process. Remember, this term is always y of x 0. Okay. So, this is any f of x y if you consider so what is this? This corresponds to our IVP y dashed equals to f of x y with initial condition. Okay. So, what is the n there? N 1, 2, so on. So, this is the Picard's method of successive approximation, and we ensure the convergence. We ensure the convergence under Picard's existence and uniqueness theorem. Okay. So, let us try another example. So, let us say your problem is y dashed equals to say 1 plus x y, okay, and let us say the condition is y of 0 equals to 1. Okay. So, we define first approximation y of x is y of x naught plus integral 0 to x. Okay. So, y 1 of x would be y of x 0 is 1, 0 to x 1 plus x y 0 of x dx. So, 1 plus 0 to x 1 plus x. So, what is our y 0 x? We have to consider the given initial condition as first approximation. So, therefore, this is 1. So, it is this is 1 plus okay. So, this is our y 1. So, now we would improve upon this. Okay. So, how do we improve upon this? So, now y 2 is y 0 1 plus x y 1 x. Okay. So, this is 1 plus x. So, just now we obtained y 1. So, that is 1 plus x square by 2. So, this is x cube by 3. So, this is y 2 x. Okay. So, now if one would, so we get the by simple substitution. Okay. So, now the question is how long we continue. Okay. So, now the question is how long we continue. So, we can refine and refine and refine. Okay. So, as I mentioned, what are the conditions under which convergence, and then when do you stop. Okay. So, the conditions under which it converges, there are restrictions on f. Okay. So, I would request you to refer to the books given in the references for Picard's existence and uniqueness. Okay. So, now with reference to this example, I would like to say when do we stop. So, when do we stop? If you look at this contains 5 terms, whereas the earlier one contains 3 terms. So, y 2 is this plus some additional terms. So, naturally if you further refine, you get some additional terms. Okay. So, keeping this in view, when do we stop? You consider at some k plus 1th stage, then you compare with the value at a previous step. If this is less than or equals to some epsilon, where epsilon is pre-assigned. Okay. So, then we conclude that the method converges, okay, up to our epsilon pre-assigned. Okay. So, for example, let us say mod of y 5 of 0.3 minus y 4 of 0.3 is less than or equals to say for example. So, now the question is whether we stop our iteration here or we proceed further. Okay. So, somebody expects no, this is not a fair enough accuracy. What do you mean by this? The difference between the solution obtained at 4th step and the solution obtained at 5th step. So, they differ by this. So, suppose we are not happy. So, then we have to proceed further, and let us say we proceeded further. Okay, less than or equals to say 0.35. Okay. That means the solution obtained 7th step, 8th step, they are agreeing up to 2 decimal places, right. So, therefore, now it depends what is our requirement. So, if somebody expects that yes, I need a solution up to 2 decimals, so then we stop. Okay. Suppose somebody says no, we have to proceed further, so then definitely we will compute further. Okay. So, this is Picard's method of successive approximations. Okay. I hope you got a clear idea of what is an iterative process, and then how do we stop at a particular iteration level. So, that is solely depends on our requirement. When I said it is on this quantity. Okay. Right. So, now having learnt the semi analytical method, we must proceed for the more numerical methods. Okay. So, so called numerical methods. Okay. So, before we proceed further, let us define formally what is an initial value problem. Okay. Let us define more formally what is an initial value problem. Okay. So, the simplest is y dash equals to f of x y. So, your f can be linear, non-linear. So, examples y dash equals to x plus y dash equals to x y square plus sin x. Okay. So, this kind of. So, now as I mentioned, this is a first order equation. So, therefore, we define more general okay. So, now so far we have been discussing only first order IVPs. Okay. So, can we generalize it? Yes, of course, we can generalize. For example, you define x, y, y1, y2, ynx. Okay. So, that means your nth derivative it is expecting up to n minus 1, right. So, right hand side is a processor which expects these are the values. Okay. So, first consider y at x naught is given. Okay. So, then y1, okay, at x naught still y1. Okay. Next y2 still at x naught, this is okay. So, like this. Right. So, what is the remark here? All the values are defined at only one point. Okay. All the values, if you see, they have been defined at only one point. Okay. So, hence this problem is called initial value problem. The reason is all the values have been defined at only one point. Okay. So, I must explain this notation little bit. So, let us understand that. So, the notation is x n plus 1 is x n plus h, okay, x n plus h. So, y of x n is y n, y of x n plus h is y of x n plus 1, this is y n plus 1, okay, right. Then y dashed of x n is y n prime. So, therefore, say y 3 of x n is, this is at x n, therefore, n and 3 there. Okay. So, now when we solve numerical solutions, when we solve any IVP numerically, we try to get the solution at particular points. So, therefore, more formal, I will give you a more formal definition little later. So, we try to get at a particular points. So, therefore, our axis, suppose this is x 0, like interpolation we divide into parts. Okay. So, this is x 1, this is x 2, x 3 and x n. Okay. So, now each this is our h step size. Okay. This is the step size. Okay. So, for example, your given interval is say 0 to 2 and say h is 0.2. So, 0, 0.2, 0.4, 1, 1.2. So, this is how we, so this is our x 0, x 1, x 2, x 3, etc. Okay. So, in general, if a b is our interval, so then if you make it into n points, so then b minus a by n is h. Okay. So, with this motivation we try to solve numerical methods. So, I would like to define more formally IVP in my next lecture. Okay. So, let us see some more physical examples, okay, where we come across ODEs or PDEs. Okay. So, one is conservation of mass and then Fourier's law we have discussed. So, now I would like to mention another example, Fick's law of diffusion. Okay. So, so this is, if V is any flow quantity, say velocity, then V dot grad C, where C is the mass transfer, okay, concentration, where C is the concentration and D is the diffusivity. Okay. So, V dot grad C is D times del square C. So, this is conservation of mass. Okay. This is conservation of mass. So, for example, if you consider in 2 dimensions, so say V bar is u v, then we have u dou c by dou x plus v dou c by dou y equals d okay. So, this is PDE, second order PDE for C. However, one must know V. Okay. So, for given u and v, this defines a second order PDE and one can solve. So, we discuss various methods to solve these second order methods as well. Okay. So, first we concentrate on ordinary differential equations, then we switch over to partial differential equations. Okay. So, we have learnt couple of physical examples, conservation of mass, then conservation of heat conduction equation, then conservation of any concentration. Okay. So, in next lecture we define more formally what is an initial value problem and then what is a boundary value problem, and then start with at least 1 or 2 methods. Okay. Thank you.